So in this video, we are going to have a look how from eye diagram, we can understand how we can improve the signal if the problem is, for example, reflection, crosstalk, or something else. Is this what we are going to talk about, Tim?
Yes, that is what we're going to talk about today.
So I think we should start with this background of eye diagram. As I said, we can create eye diagram from all the kind of signals, correct?
Hmm. Yeah. Let's see, let me walk you through the generic eye diagram creation.
Mm-hmm.
And should I put it into presentation mode to get the animation?
Okay, yeah. If you have animation, we can try to do it.
Yeah. Typically when we transmit digital data, we are sending in pseudo-random binary sequence because we don't know exactly what digital signal is coming in. So we try to emulate what all the possibilities. And a lot of times, here are some key terms, your data rate and unit interval. Once you have these 1, 0, 1, 1, 1s, it's actually a voltage waveform. And what we can do with this voltage waveform is using our knowledge of unit intervals and create different slices of these unit interval. Then overlap these slices to create an eye diagram. Now this will give us a lot of different information, especially when you have an open eye at the TX. If you take a slice in the middle, Robert, then you can see a 1 and a 0. You can clearly distinguish. But on the right-hand side, after the signal goes to the channel, the eye is collapsed, then you'll know you have a signal integrity problem. So that's why we
Oh,
can apply this eye diagram more than just to memory.
okay. So to make it very simple, basically, in one eye diagram, we can
Hmm.
see uh, many transmissions in our data lines in
Hmm.
just one single moment, and
Right.
uh, and we can see all the kind of variations between these transmissions just in this one picture. And that's why this eye diagram is so important, because we can see it's not only, we are not looking only once at one signal, we are looking at all the kind of signals, how they actually look in a transmission line, correct?
Yeah, exactly. It's the overlapping part that's most important. You're taking a very long signal and combining them into one single picture.
So basically we can see in, for example, some of the transmissions, the voltage could be a little bit lower, or in some of the
Hmm.
transmissions, the edge wasn't very sharp, or these kind of signals. And then when you say the eye is open or closed, then
Mm.
basically that's the part in the middle.
Yes, that is the part in the middle, and that's a very good question. Typically, you will have a eye mask in the middle to label it as a keep out. So I'm marking it on the left here.
Hmm.
Usually there will be some sort of a diamond or a shape in the middle. If anything were to come inside of this eye mask, then you'll be violating the eye mask, then your eye will be closed. So that's
Hmm.
a good point.
Does
That's
not,
one of the metrics that we use.
this means like some of the signals were out of specifications.
Yes, exactly.
Oh, cool, perfect. So I hope now everyone understand how we create this eye diagram. I think we can create eye diagram. There should be something on the scope, correct? You just press button or something, and you will ask
Mm.
like create eye diagram or something.
Yeah, exactly. Uh, Keysight scopes too, it doesn't matter what scopes you're using. In the background is doing the same thing, using a very long time domain signal and slicing it so that you can create an eye diagram. That's a very good observation.
And it's same for simulation. So when we for
Yes.
example create our channel and we would like to
Hmm.
simulate it, then basically in simulation we run all the kind of random ones and zeros, and then
Yes.
simulation will create the eye diagram from this.
Right. Very
Okay.
good.
Uh, okay. So what do you have on the other slides? You can make this smaller again.
Okay. Yep. I'm gonna do.
And so we understand. Oh, okay. So what I would like to mention, I can see here TX and RX. So
Hmm.
basically, this means that we can apply this on any kind of signal. It is any kind of signal which has output and input. Yeah, and so it can be slower signal, it can be faster signal, and this is very often used also for like very fast signals, because that's when the eye diagram is very important, and all the kind of losses and everything can be happening. But as I said, all the kind of connections in our PCBs are almost always output and input. That's why we are talking about this and why we are creating this video, so everyone can understand the eye diagram. So what can we see from eye diagram? Can we go back to the page number 12? What we can see here and how we can improve it.
Yeah, in this picture we can see three different things. In the middle is the red reflection, and the gray is some crosstalk on the top here. An orange would be the frequency dependent loss. And we can dig a little deeper in each one if you're ready, Robert.
So basically, if there is reflection in our transmission line, then the eye can be closing. Or if there is crosstalk, then the edges of the eye will be wider or something like that. That's what it means. Yeah?
Right. If there's crosstalk, you will see it somewhere on the top or in the transition area, and that depends on how long the transmission line is in the crosstalk region.
And then if there is frequency loss, then the shape will be changing, or what will be changing?
Yeah, if there is frequency dependent loss, then it is the rise time degradation coming from this angle. I'm drawing in red here. So you can see this is typically we want a rise time in blue that is very sharp, but because the frequency dependent loss, the sharp edge is become the red one, the slope. Yeah.
Okay, and the reflections, they are again, the reflections will be making the eye smaller.
Yes, and the technical term for the eye being smaller is called a vertical eye collapse.
And the reflections are not going to do same?
Same in what
I mean,
sense?
reflections can also close the eye, correct?
Yeah. So that will be the vertical eye collapse, exactly.
Okay. So what do you have on the next slides? We are going to have a closer look how this is happening, yeah, correct?
Yes.
Okay.
So since we're not using animation, I'll walk you step by step.
Okay.
So on top here, if we have a moderate loss channel with no discontinuity, we should expect a pretty good looking PRBS and nice looking eye.
I think we should maybe explain what does it mean, no discontinuity.
Yeah. No discontinuity means the entire channel traces here is uniform. There is no impedance difference. It's all, say if it's 50 ohms, it's all 50 ohms throughout this channel. That is the meaning of no discontinuity. Now, if you compare the top to the bottom, I purposely make a big discontinuity in the middle here. It lowers, it's a wider trace, so it has a lower impedance, which means there will be reflection for sure.
But now maybe people may think like, why would I make my track wider in the middle of the track? So this only is used for illustration, but in reality it can be, for example, via, correct? Because via
Maybe
will
any
have
type of
different kind of impedance, for example. Yeah.
Right. Any type of impedance discontinuity can be modeled. That's a good point. This is more for a demonstration, but you're right, Robert. It could be a via, it could be
connector.
A pad, it could be a connection. Yeah, a connector too, yes.
Yeah, okay. And then what will happen? Because there is no picture.
Yeah, so there's another picture over here. So there's interface number 1 and interface number 2. As the signal travels from the left over here, from the left to the right, it encounters the first interface. Then parts of it will be reflected, as shown in the purple arrow. Part of it will be transmitted. The same thing will happen in interface number 2. Now, if you notice, the the transmitted, oh, sorry, the transmitted is smaller than the original one.
Mm-hmm.
And that's why I said on the right here, one expect the received amplitude to be smaller on the right. It's because all the reflection in the different interfaces.
Mm-hmm. But is that bad?
No, it's good. So that's why. So next slide. Oh, next slide. There's and actually. There's another thing that would happen is if we look at the interface again, at interface number 2, some of it will be transmitted, this one, and some of it will be reflected as this one.
Mm-hmm.
And this reflected one at the very bottom would meet our interface number 1. And the cool thing would happen because since there is another discontinuity,
Some
it
of
gets
this will
reflected
reflect
again.
again.
Yes. That's why on the right I said, ooh, because the shape will be deformed since there are multiple reflections.
Mm-hmm.
Finally, what's going to happen is this slide, where in circle in red, the change of amplitude, vertical amplitude, and the shape creates this blue eye diagram as compared to the
Mm-hmm.
red one. We just talked about reflection, and how do we fix them will be the next question, right? Since we
Yeah.
know it's the impedance on the left here, discontinuity that's causing the problem. What we need to do is remove it. That's why on the right-hand side, I said the fixes is you have to locate the discontinuities and match it with the channel impedance.
Mm-hmm. So basically, this means exactly what we mentioned at the beginning. For example, when you are routing traces on your PCB, then the traces, they should always have 50 ohms. For example, even if you are changing layers, then you should try to keep it always 50 ohms, and then the quality of the signal will be the best.
Right. You need to have a controlled impedance line.
Mm-hmm. And I think you have a simulation where we can actually have a look and see the reality.
All right. Here we do have a simulation setup. Now I want to perform rule number 9, where we anticipate before we measure or simulate.
But before we continue, maybe we would like to explain a little bit what we see here. So how we actually do the simulations. Maybe everyone who would like to simulate their PCBs, their tracks, they would like to do maybe something similar.
All right, this is a schematic where we set up to do an eye diagram simulation. On the very left-hand side, we have a TX transmitter,
Mm-hmm.
which will give you different data rate and rise time, so you can specify also the voltage height.
Mm-hmm.
Then
Is there something so special about this transmitter, or you need to assign a model, or how does it work? You can use any
good question.
transmitter?
Yeah, this one is a generic
Mm-hmm.
transmitter, but if you do have your special model like the IBIS AMI models, we will always also able to do that here,
Mm-hmm.
but not in this component, but a component.
Mm-hmm.
Then coming to the center, we have in the middle, this is the channel, what we call the interconnect, or the channel in the middle.
So this is, for example, the PCB, traces and vias and all these kind of elements in the way where the signal is traveling.
Very good. Then on the very right, we see our RX. That's where we'll get our signals.
Mm-hmm.
But since in simulation, we have to tell the software where to probe. That's why we have these two things. On the left here,
Mm-hmm.
you have an iProbe inside and an iProbe on output.
Mm-hmm.
That's the setup.
So
now to make
in the result of the simulation, there will be basically two eye diagrams. One will be measured directly at the output of the transmitter, and the other one is measured on the input of the receiver.
That is correct.
Mm-hmm.
And if you notice in the middle here, Robert, I have specifically, since we're talking about reflections, I have created variables for different variables on the impedance and delay of these 4 different line segments. And once we simulate, so the first case number 1, as we've seen here, and we have a case number 2 at the bottom here. The case number 1 is all 50 ohm lines, which means it's a very controlled impedance line environment. We should see the eye as open as it can be. That's what we expect.
Highest quality signal.
Exactly.
Okay. So let's have a look. Let's simulate this.
Let's simulate this. We'll hit simulate. And voila, as we expected, on the eye on the input, on the top left, and the eye on the output, looking very good. In the bottom, with discontinuity, since we're doing case number 1, no discontinuity, with discontinuity is the same because we're looking at 50 ohms throughout.
I don't. So why do we have 4 of them? I understand.
Oh,
yeah.
So in this case, I'm comparing on the top is no discontinuity.
Oh,
and the bottom
okay. So,
with
so the
discontinuity.
second time when we put there something special, we would like to compare it with this original. Okay.
Yes.
Okay. So let's do the second simulation.
All right. So we will go back to our schematic. We will enable our case number 2. We'll hit simulate.
So what is different in case number 2? Oh, I can
Case
see
number 2,
line 3 is 75 ohms.
Yes, I threw in different impedances, continuities in the middle and expect the eye to be more closed. And sure enough, at the bottom, if I zoom in to the bottom here.
Wow.
Yeah, on the TX, it's very funky.
So just like changing small element in your trace, and this is what will happen.
Yeah, on the TX side, because multiple reflections, and on the right, we can see, Robert, you mentioned the vertical collapse right in the middle here. Yeah, we can make it worse if you want. Let's make it worse, shall we?
Oh, wait. So on the right, that was the input. This is the input. Yeah.
This is the output. Yes.
On the left, that's the point. Yeah, on the left, that's measured on the transmitter, on the output of the transmitter, correct?
Yes.
And on the right, that's measured on the input of the receiver.
I see what you mean. Yes.
Okay. So the output of the transmitter looks like a very, very bad.
Yeah, because the multiple reflection coming back and forth.
It's not important because we are not really reading signal from the output of the transmitter, but it's very interesting to see like how bad it looks.
Yeah.
So this is actually this may be very important. Sometimes people may think it really doesn't matter where they put the probe, but maybe no. Maybe they always should measure where they are reading the signal.
Right, and sometimes if you have a lot more voltage than the transmitter can handle, it can goes into a special state, and that we can break the device if it's over the voltage range.
Really?
Yeah.
Okay, so zoom in again on the reading on the input, on the other one on the right side.
This one.
Okay, so I can see what is happening. How would you like to make it worse? We can make it worse.
We can make it worse by introducing more discontinuity. Right here, the blue is where we see the voltage reflections. If we go back to our schematic and change some of the impedance, we can make it worse. Right now, we have line 3 is 75 ohms and line 4 is 50. We can change line 3 to be 80 and line 4 to be 25. Oh. Okay.
Same idea.
And we'll hit simulate. We expect it to be worse because the difference is bigger, right? And let's see. And sure enough, we broke it.
Wow. Show the other one.
Yes.
I'm curious how the other one looks.
Yeah, the other. Oh, it should be even worse. The world is collapsing around us.
Okay, let's go back to your presentation. So this was
Okay.
about reflections. What was the second
Mhm.
point? What else we
The
can
second point, the second one is about crosstalk.
crosstalk? Okay.
Yes. Right. With crosstalk, what we'll do is we'll set a controlled environment where everything is far away. In this case, my far away is 10 trace width apart.
Hmm.
Right here
But
is
in
10 trace
reality,
width
when
apart.
we are doing layout, that it can
Hmm.
be, these are basically three tracks routed close to each other,
Yeah.
and crosstalk will happen when they are routed very close to each other. And we are going to
Hmm.
have a look how the eye diagram is going to look when we route the tracks very close to each other or when
Right.
we put them a little bit further.
Hmm. That's the idea. That's right. Right. With the 10x trace width apart, everything looks good. I number one is fine. I number two is okay. I number three is also looking good.
So
But
basically in this case, we are running signals in all the three tracks
mhm,
at once. Yeah.
yes, all at once at the same time.
And basically, if there is something wrong, then probably the worst will be the middle one because it's going to be influenced from the left and from the top and also from the bottom.
Hmm.
Okay, let's have a look. I'm curious. I'm curious.
Let me move. And what's gonna happen is we're gonna bring them close.
Yeah,
Let
yeah,
me
yeah,
let me
yeah.
try something. Let me try annotate. Maybe this will be better using. Well, how close is close, Robert? What do you think? How many trace width is close?
Mm, I know I've done some just recently. I did video with Yuri, and
Mm,
we were looking at the fields around the
yeah.
tracks, and I know for 5 times trace width it was kind of okay. Three
Mm,
times was worse, was a little bit worse, but one time was like bad, really bad.
yes. That's why we pick one time as the closeness here.
Hmm.
And in this case, we're looking at the foreign crosstalk where we send in 0 to 1
Hmm.
stimulus on the left.
Hmm.
Then we'll observe what's coming through the RX
Hmm.
on the right, and the rest of the lines are terminated.
Hmm.
What's going to happen is when we send in this 0 to 1 pulse, is that this voltage would have some current waveform. Now, because this voltage is from signal S to R, signal to return, you'll have a clockwise current loop. Now, I don't know about you, Robert, but me as a person, I don't like change. I always resist change, and nature does too. So as the adjacent trace sees this clockwise current loop, it says, no, I don't like it. So you're trying to counter the clockwise. That's why you have the counterclockwise current loop.
Hmm.
That is from the return to the signal.
Hmm.
And they both will propagate down the line here. You'll see in gray on the right and the blue at the bottom, that is the crosstalk voltage because they are close to each other.
Hmm. So basically, very simply to explain what we
Hmm.
see here is when we run signal through
Yes.
data 6 lines, then
Hmm.
at the point where the signal is changing the levels from 0 to 1, there will be this crosstalk or this small dip generated on the other
Right.
line, data 7.
Yes, yes, yes. You're totally correct. It's in the changing of this 0 to 1 that's inducing this current loop,
Hmm.
and that's going to propagate down the
Yeah,
transmission line.
because the edge
Good
is
job.
traveling from the transmitter to receiver, then
Hmm.
also the crosstalk will be traveling together with the edge.
That is correct. That is correct.
Okay.
Very good. All right, let me.
And we can see this in eye diagram. Yeah.
Yes. Let's see. So we'll go right here. Because of the crosstalk we've seen, the signature in a usual PRBS is like these blips would show up. Now, since we can create eye diagram from the blips, we can do the next slide where it shows up in a transition.
Oh, so this is how it looks in eye diagram.
Yeah. But now, Robert, I know what you're thinking. Before, I was showing you this one, right? But now I'm only showing you in the transition. Right? Why is that? Any guesses?
How did you know I'm going to ask this?
I guess I've been asked this question enough.
It was exactly my question. Like why the crosstalk is showing up where the lines are crossing.
Very good. Okay.
Because of
So now
trigger
we
or
can.
something? I don't know.
Ooh, I- very good. So the first thing is, let's take a look at our original channel. They are of the same length, right? Typically, we route the traces the same length, and this will be another reason why we want to do that. So if they're the same length, everything looks fine. But as soon as you have different lengths, the coupling will still happen, but the crosstalk voltage and signal, I'm gonna mark it on the right here, here, they would arrive at different times. And it's the length difference that's causing the voltage arriving at different times that would collapse the eye vertically. So the reason why that would happen is this. The same channel length, it looks like this, only happened in transition. When they have different channel lengths, it happens. You can mess with your designer friends, SI engineering
Oh, I
friends.
understand now. I understand.
Yeah.
Because when they are exactly same length, then the
Yes.
crosstalk is always happening where the edge is.
Aligned. Yes, that's correct.
That's
Yes.
why we see it at the moment where the edge is. But if the length is different and the crosstalk will keep traveling, then
Yes.
we can actually see what is also the difference between the tracks, in the length
Right.
between the
Right.
tracks.
Right. I'm gonna show you a very, very bad case where everything is different lengths. Then you will see I6 from TX data 6. It opened up in the middle, and I7 somewhere in the middle, and I8 looks funky. So this is another motivation to keep all the channel the same length as you can. So if you have crosstalk, you would not collapse the eye vertically.
Huh, this is interesting. Okay, and so what do you have on the next one? Because I think we also have simulation for this, correct?
We do have simulation for this as well. And here is just a summary of what we talked about. We have if you have peaks in eye transitions, I'm looking at the bottom left here. If you have signs in the eye, it looks like this. There's eye transitions or peaks in the eye. You can kind of tell it's gonna be crosstalk from adjacent channels. To fix it, you want to move the channels as far as practical if you can. You want to maintain the same channel length so you can very well isolate just only in the transition area.
But I think in
Yeah.
reality there are two kind of crosstalk: far end and near end crosstalk. So what will happen with the second crosstalk?
Ooh, that's a good question. We can go back to our diagram here. Right now we're looking at the far end
Oh, there
crosstalk.
are terminations on both ends. Okay, so the other one
Yeah.
will not. It will die at the
hmm
transmitter side.
Right. The near end, so we've been looking at the far end on the right hand side. The near end would be, as we couple, this will be the near end. So this is the what we call next. Very good. Yeah. Now you can imagine if you have a TX and a TX on this side, TX, and Rx receiver on this side, this near and crosstalk would actually impact the eye diagram on the Rx.
Okay, I understand. And in reality, if your trace is not correctly terminated, if there are these impedance changes, what we mentioned before, then you would get even reflections, and the crosstalk may travel from one side to the other one, and then
Oh
the
yes,
eye would look even worse.
exactly. So everything could happen all at once.
Yeah, okay. So let's have a look on this simulation.
All right, let's go back to the simulation. Let me bring up the crosstalk simulation.
What do we see
Shall
here?
we, shall we walk through the setup again?
Yeah, definitely.
All right. So first on the left, we have similar TX setup right here. On the right hand side, we have similar RX. But in this case, I'm only having one RX. I want to see how bad the eye would look like. And the other one are terminated properly as well as this one. In the middle is the channel. Oh, in the middle is the channel. And if I zoom in a little bit, let me see if I zoom in.
So this is our PCB basically, yeah?
Yes. If I zoom in, we say if you have routed 3 different traces, and right now the spacing is 5 times the trace width. Yeah, Robert, you mentioned the work you've done with Yuri. 5 times is, it's kind of far enough, right?
Yeah, it should be.
Yeah, so we should expect a little bit, just a little bit crosstalk, not too bad. And let's hit the simulate. We should expect the eye to be pretty open. And
I'm curious. So now we will see 4 diagrams, because I think there were 3 on the... Oh.
Yeah, we'll see 6, yes.
6.
We'll see 3 on the left and 3 on the right. And yeah, you made a good observation. Since everything is running all at once, the middle one would get more from both top and bottom, as we see. Since it's five trace width apart, you get a little bit at the transition area, but not too much.
And we can see the middle is kind of clear. That's interesting. Yeah, that's exactly what we explained. If the length would be different, then these bumps would move a little bit.
Ooh, yeah, we can explore that too.
Okay.
And let's go back.
Put them
kind
closer.
of spacing
Put
do you
them
want?
closer. Yeah.
How close?
1.
How close?
1.
1. Okay, let's do 1. And we should expect the eye to be pretty close at the transition, right? Because the length are all the same.
Yeah.
Okay, and let's see.
So basically now we are simulating situation when the tracks are routed close to each other. Just the distance between them is 1 width.
Yes, apart, yeah. And sure enough, look at that.
But this is interesting because on the left, that's the go on the left.
Yeah.
So now these are the diagrams probed close to the transmitter, correct?
Yes.
Yeah, and you can see they're very nice because good termination and everything, and because the crosstalk what we are looking at only travels on the other side.
See, now we're looking at this eye. Let me ask. The red I've created here. The red is the ideal. Now we will see the blue. What we simulated is a little thicker than the red. Can you give me an idea? Give me an idea what that could be. We talked about this term.
I don't know.
It's some kind of crosstalk. It's the near end crosstalk.
Yeah.
Yeah, this is the signature of the near end crosstalk.
Oh, because the near end crosstalk is wider?
Yeah, it would make the eye look thicker, the different levels look thicker. So that's the signature for the near end crosstalk. And on the right, yeah, we looked at the signature of far end crosstalk. But since they're very close, it gets very crazy.
Wow. So the middle one is really bad because there is influence from the track on the top and also on the
The
bottom.
bottom, yeah, that's correct.
What else we can read from eye diagram?
Yes, we have covered the first with reflection, second one was crosstalk, the third one would be the loss. So let me save and close my windows and let's go back to the presentation on the third part. That is the sign of frequency dependent loss. And if I want to be more specific, I'll be talking about this rise time degradation.
Mm-hmm.
And what the root cause of this is, if we compare an ideal lossless case, let me bring up my annotate. There we go. If we bring up this lossless channel with beautiful PRBS and a lossy channel, we convert them to the frequency domain to the right here. You will see that the circle in the red, the spectrum of the lossless channel and the lossy channel would tell you that as frequency goes higher and higher, more loss is being applied to the channel, which tells you that.
Go ahead. Go ahead.
Yeah, which tells you that the channel is a low-pass filter.
Okay, I would like to clarify so everyone understands what this means. So basically, when we are talking about this lossy channel for different frequencies, it means, for example, in this specific case, faster and faster signal is traveling through the tracks, then lower and lower and lower signal will arrive to the receiver, correct? For higher frequency, lower signal will arrive to the receiver.
Yes, in a case where it's losses, where in an ideal world where there's no loss,
Then
you
the
send
signal
in
which is on the transmitter would be exactly same
like the
which is
same.
received on
Yes,
the
yes.
receiver.
In real life, it's in blue. Real life is you have a lossy channel, it would be degraded. Yes.
Yeah, and the thing is, it's how much it will be lower. It also depends on frequency. So for lower frequencies,
Yes.
the loss may not be so high, but for higher and higher frequencies, the loss will be bigger and bigger and bigger. So basically,
That's right.
that's why the shape of the signal is also changing, because the edges, they actually contain a lot of different frequencies. The edges are created from many different frequencies, and that's why the edges are a little bit different, because for higher frequencies there will be bigger loss, for lower frequencies or smaller loss. Correct?
Yep, that's correct. That is correct, yes.
Okay,
Very
so what
good.
does it mean?
All right, well, let's take a look at the next step, right? From here, we have this lossy channel and the insertion loss. The insertion loss looks like at low frequency, close to 0 dB, what we expect. And as we go higher and higher frequency, you have more lossy. What happened is this frequency dependent loss creates this, in red, this rise time degradation. Now, Robert, I focus on the frequency dependent loss. The natural question is, well, how about frequency independent loss? How would you expect that to change the eye? Would that degrade the eye height, eye width, or would there be any rise time degradation?
Everything would collapse exactly same, so it would be just smaller.
Oh, yes, that's very good. That's very good. Exactly what Robert said. If we have a constant loss over frequency, only the amplitude would be smaller. We're shown here only the amplitude is smaller. The rise time degradation is not there because the beautiful thing is the constant insertion loss. And this is actually the key of equalization. Typically, we have the channel looking like this.
Oh,
We know
and
that,
then you move it back.
yeah, if we have another channel that does something like that to make the entire thing flat, then your eye height will be lowered, but no rise time degradation.
We should explain this. So when you mentioned how is it called again? Equalization.
Equalization, yes.
So it means basically for very fast signals, the signal is kind of corrected at this when it is received, and this is exactly, for example, one of the kind of corrections what we would like to do. So for different frequencies, we would like to amplify the signal. So basically, we get the constant loss for the signal. Correct?
Yep, exactly. Exactly. Very good. And that's why we want to do equalization, how we fix, like you said, how we fix the signal. We can correct the signal.
But then when you are setting up these equalization parameters, you need to exactly know this loss graph, no?
Oh, yes. So a lot of times, the technical term would be the back channel. The transmitter need to know what the channel looks like before it can do some correction. That's a good observation. Yeah. Very good.
Okay, so do we need to go to the next slide or the previous one? Did we finish the
I think
previous
we
one?
go. I do have simulation for this. You want to see the
Oh,
simulation
yeah,
for this?
definitely.
Simulation for this. All right. And one thing about loss is the longer the trace is, the more lossy it's going to be. Here is a simulation. It's quite simple. It's similar to what I've been doing. We have the transmitter on the left hand side.
And
Transmitter.
we never mentioned the filter, or what is it there, the second component?
Oh, all right. The filter in the middle. The filter in the middle is my way of creating a real life signal. If we look on the left, this component, this transmitter component has a rise time that is from 0 to 100, which is not quite a real rise time. It's a linear from 0 to 100. It looks something like 0 to 100, which is not real life. In real life, it often looks like a error function where it looks, let me see, like this, smooth, and this way. Now to create this smooth function, I use this bezel filter. And given the Nyquist frequency, I'm able to connect these two.
Okay.
Good question.
I was curious.
The little nuggets here and there. And right now we have a trace that is, say the track you're running is 3,000 mil, that's 3 inches.
And how do you specify this one? So you specify the loss there, or?
The loss will be specified in this trace. It has its own substrate. If I can open it up for you, its substrate looks like this. Let's see, it has the substrate right here. It's an FR4 prepreg and a solder mask with copper on top and bottom. And all the loss metric will be inside. So if you change the FR4 to a Mactron 7, then the loss will be definitely less.
Okay, so basically we are simulating this for FR4.
Yes. This is the FR4 trace. Now, my advisor, Eric Bogatin, always asks me, Tim, we have to practice rule number 9. What do you expect the loss to be? And here is where we kind of calculate using our rule of thumb. The rule of thumb here is you have 0.1 dB per inch per gigahertz. Now with the 3 inches, we have 0.3 dB. Now the gigahertz, we have to go to the data rate here. Data rate on the left we see is 32.
So 16 gigahertz.
Exactly. So 16 multiplied by 0.3 is about it's a 4.8 dB at Nyquist. And I want to clarify here. Typically 4.8 at Nyquist, the eye should be open. It's when it gets to 10 dB at Nyquist, I will be closed, just in general. So we should expect, in this case,
good quality
an open
signal.
Yes, pretty good signal. And right now, let's see there on the right hand, the receiver has DFE enabled. So we'll see if this eye is closed, eye number 1, the channel eye is closed, the equalized eye will be open using this equalization technique, decision feedback equalization. To simulate, we expect the eye to be open, so not too much needs to be done by the equalization.
Again, I would like to point out equalization is only happening in very high speed stuff. Normally, normal standard slower boards, they don't have equalizations.
Right. Yeah.
Okay, it looks good.
Yeah, as we expect, because we have only 4.8 dB and Nyquist, the eye still looking pretty good, so not much the DFE needs to do to open it up. Now, Robert, we can make it really bad, so we can see what equalization can do.
So how long
Shall
do we
we do
need to
that?
make it?
Ooh, that's a good question. We said right now at 4.8, the eye would be open because at 3 inches. If we kind of double it, we make it 6 inches, then it will be 9.6, close to 10 dB of loss at Nyquist. So we should see the eye close up significantly, and DFE would do a lot of work.
Okay.
Shall we do that?
Yeah, definitely.
So now I've doubled the length of this channel, and we should expect the eye to be more closed, and DFE would do more work. And the survey says it's longer, so it will take a little time to characterize.
It takes longer.
Yes. Ooh, sure enough.
Oh.
It was more open. Now the eye is more closed. And DFE can work hard.
It
If you
still
compare
looks
the
the
two.
same.
It's more open here. Oh, you can see here's a comparison between the eye opening. The red is before, and the blue is after. They definitely open up at least 100 millivolts on
So
the
this
top
is
and
what the
bottom.
equalization is doing.
Yes.
So basically, we went for everyone who is not using inches. So we went from 3 inches. It's like what, like 6 centimeters? I don't know.
Yeah, 6 inches. If you multiply by 2.5, that's about 77.5 centimeter to 15 centimeter. Yeah,
So
around that.
this is 7, and this is 15. So it's not very long track. It's
Yeah, but so the FR4, typical, you can expect. I think that's why people are going into low loss materials. It's just like it run even longer.
yeah, but we are talking about 15 gigahertz signal. So
That's true. Yeah. That's right. You're correct.
okay. So what else do you have in your presentation?
Let's see. We go to the presentation.
You know, when I had a look on I never really thought about these things like spotting out the reflections and crosstalk. And thank you for preparing this presentation.
Yeah, happy to help. Yeah, it took me a while, but then you are like the detective now, signal integrity detective. You'll be able to look at these different clues.
Not only me, everyone who is watching will be now.
Yes, everyone can be a signal integrity detective. Well, I think this will be a good time to mention before we were increasing the length to break the channel, right? So we want to save the channel, we want to reduce the length. Here's an example of if I start, my starting length is this much, using the eye mask we mentioned, it's closed. Take a step back. This one is an example where 25 millimeter is actually kind of long. It's a triplet example. If we reduce it to 18, then we are clearing the eye mask.
So
now
it's
finally,
again we have to mention, so 25 millimeters, that's 1 inch. No, a little bit less.
Yeah, it's
1 inch. Oh,
yep.
Okay. Yeah.
Yep. And then here, if we change it to 10 millimeter, then eye is really open.
Wow.
But now, after today, we are all signal integrity detectives now. You can tell there is
Reflections. Crosstalk.
Yeah. Yes.
But it can be also reflections, no?
Yes, it can also be reflection. That's right. Yeah. So you have two possibilities, then you can test it out in your channel. Very good. So here is a summary of what I've done so far. The transition edge slope is slow, so there we have rise time degradation. The root cause is a lot of frequency dependent loss from the channel. First thing to do, if you can, reduce the channel length.
Or
If you
you
have the
can change
money,
material.
exactly.
If you have money, yeah, as you say.
Very good. Yeah. And here is a summary of what we talked about and the root cause and fixes. Very good.
And that's it, yeah, I think.
Yeah, if you want to learn more about equalization, we can do a little more.
Oh, we can mention this. So maybe someone is interested to learn a little bit more about equalization.
Mhm. We can do a part
I'm
two.
also curious. I've done one video where we talk about
Uh-huh.
this, so I know a little bit.
Yeah.
Uh, and I was actually very surprised it can be so effective, because I
Hmm.
think for like very fast signals, you can lose a lot of signals, and
Oh yeah.
it only look like noise at the receiver, and it's still
Mhm.
able to find out what kind of signal
Recover.
actually. Yeah.
Yeah. And the fun thing is there are a lot more standards now. Like say take PCIe for example. It's known as a closed eye standard. You're actually expecting an eye to be closed and using the equalization at the RX to recover the eye.
Wow. Okay, we can explain a little bit more what equalization means. So you have some slides for this.
Yeah, right. Yeah, so far we've discussed how the eye would look bad if the channel is too lossy. Here on the left we see, let me show you this one. We show right here. Here on the left, 1 and a 0 can be clearly distinguished, but after the channel, the eye is closed. Now what we're talking about, Robert, is equalization. If the channel loss is in blue, then the eye is going to look like the one in the background, blue
Hmm.
eye is closed. If we can, as you suggested, have a frequency independent loss where it's the same throughout the frequency, we would not have the eye collapse.
Hmm.
That's what we're trying to do. It's equalizing the frequency spectrum.
Hmm.
Yeah. And there are many techniques, and the top three are, let me go through the top three. The three are CTLE, FFE, and DFE.
Hmm.
And we can talk a little bit more, but I have kind of noted here what's special about them. There's CTLE, continuous time linear equalization, where it can actually be implemented by putting capacitors, inductors, and resistors. So it could be a purely analog design.
Hmm.
And in the middle, we have V4 equalization. The special thing about it is it handles pre and post cursor. And we'll talk about these pre and post cursor a little later. And for decision feedback, it's the only nonlinear one, and it can only happen at the RX because we're making decisions. So that's the
Oh, I didn't
overview
know you can
of,
have this equalization also on the transmitter.
yeah,
I
yeah.
didn't know that. I learned something
Mm,
new.
good. But then the thing is, you still need to know what the channel, that's why we will go through a training sequence where the TX will send an RX a sequence of signals and send something, the RX will send something back through the back channel. So then the transmitter would know what the channel looks like and
Hmm.
configure the equalization accordingly.
Before we continue, actually, uh, I remember when I was creating the previous video on this topic,
Mhm.
one of the things what was very interesting was this equalization. Actually, sometimes it may need to consider also the previous bits, because the signal can be influenced with the bits which were running through the channel before. That was interesting.
Ooh, that's exactly what we call an inter-symbol interference. So here's an example. It's fun that you brought that up. Typically, we look at the eye as, we have the PRBS and we slice it. And you can also look at a single pulse, or what I call a blink of the eye, where you send all zeros and only a single one. If you do that on the TX side, it looks like this. But the RFs and on the receiver side, it will look something on the right-hand side. One thing to note is if you transmit only a 1, you would have spreading because the channel loss. That exactly what you said. The 1 would spread to previous bits and post bits, and that's when we call inter-symbol interference, where the bits are interacting with each other.
So the ones what we are talking about, they are not going to correct this, or are they?
Ooh, yeah, okay. So that's the next step is the pre and post cursor. We're making
okay, so that's what it means.
yes. Okay, so let me clear all my rows. If on the left here you receive an eye, right? You have the cursor in the middle. Usually we use the maximum as the point as a cursor. Whatever happens before that, we call it the precursor. It happened after is the post cursor. And in simulation, typically you have receiver models that has ability to perform equalizations, like IBIS AMI models.
Oh, and I just remembered there was another thing what was very interesting from the video what I was doing before. If your very high speed transmission doesn't work, it doesn't mean the PCB is wrong. It just may mean you don't have the correct settings. So
Sure.
So when you create these, or when you do these very high speed signals,
Right.
maybe the problem is not in hardware but in the settings.
Oh yeah, for sure. And the newest PCIe 7 standard, it has let me think, 7 different CTLE presets, 11 FFE presets. So it's a matter of configuring these different knobs so that you can optimize your receiver eye.
So how do you do that? That's why there can be then the back channel, and basically it can be done somehow automatically.
Right. So there will be optimization techniques in software to go through the optimization process and find out which presets give you the biggest eye.
Okay, let's go back to presentation.
Yeah, and we can go talk a little bit about CTLE. CTLE, I would say, it was the most straightforward in the frequency domain, because exactly what we're talking about is if our desired response is a flat throughout frequency, CTLE on the right here, it's exactly giving you that. It has a complement high pass filter that would open up the eye. So here in the middle is what it looks like. Yeah. From the blue, no equalization, to equalize.
Nice.
But now you notice they're all on the same scale. You notice
Yeah, it has
the
to be
amplitude
lower.
reduced.
Yeah, it has to be lower. Yeah.
Yes, but if you have the money, you can have some gain. So you can actually be bigger.
Okay.
Let's see. Next step is FFE. FFE. FFE looks something like this. So we'll walk through just a little bit from the left to the middle. We mentioned in the voltage maximum, we'll call the cursor. You have pre and post cursor. What FFE is doing is trying to pre-distort the pulse in the transmitter side. So in the pink, I've shown you that there are some ISI leakage.
So you
FFE
put
says,
it lower.
if I know there's going to be ISI, let me prepare for it. That's why we have these two negatives over there. And if we zoom to the bottom left, this is how in the TX it will create. We started out from a single pulse. You go through 1, 2, 3 different tap values with different delays. delay meaning unit intervals. You sum them together, and you have a pre-distorted pulse.
But does this influence, like, because if you put there delays, it means your signal will arrive a little bit later.
Well, this happens in the transmitter. So the transmitter creates this signal knowing what the
Yeah,
channel
I
looks
know,
like.
but I mean, if your transmitter would have like multiple lines which has to run exactly at the same time, then you would need to do it for all the transmitters exactly same way, correct?
Yes. And yeah, so then there will have to be some mechanism to keep all of them, all of them aligned at the TX and the RX side. It's a good observation. Yes.
Okay, I like the first picture because from the first picture, yeah, I can see what actually happened with the signal. You put it a little bit lower, so you minimize the edges which are going out from the red box. Okay.
Well, that's FFE. Now we can look at FFE from the time domain to the frequency domain because we know what we're trying to do is equalizing the frequency spectrum. We'll notice on the right here, this is the frequency domain in pink, FFE. I've circled in green here that high frequency content is boosted by FFE and the low frequency content is reduced by this pink. So this is a big learning for me because I've always looked at FFE in the time domain. It was until I moved things to the frequency domain I learned, wow, it is.
Yeah, because
Equalizing.
the top is a little bit lower. Top of the signal is a little bit lower, so the biggest or the lowest frequencies they need to be smaller.
Right. Yep. Yeah. Oh, and here's another observation. Since you have different tab values, right? It's trying to keep the TX the same. You're using the same TX power, so the tab values are restricted so that you're not using too much power.
Interesting. Okay, and the last
then we can
one.
go. The last one will be decision feedback equalization, which is the funky one. What TFE is doing is it says if I'm seeing a 1, I will emphasize the next 0. So to demonstrate this, here's a 0, 1, 0 pulse. Now
Yeah.
since the...
Yeah,
Go ahead.
go ahead.
Yeah. Since the equalization sees a 1 here at the cursor, the pole cursor is trying to emphasize the next 5 zeros by dropping down the voltage. Yeah. And these tabs are all unit intervals.
Okay, I don't know where this is going.
Well, see, that's the thing. Because if we see a 1, you emphasize the next 0, what you can do is creating a pulse like this. And altogether, if you do it for the 1s and the 0s, you would, the same thing, you would actually boost all the high frequency components. Essentially, at the end of the day, you would achieve this eye diagram at the bottom here, but with very distinct DFE signature. Because the boosting and the emphasizing the next 0.
Okay. So next time I will know why the eye diagram looks like broken.
Exactly. Adding to our signal integrity detective skills.
Okay, so we are almost finished. Yeah.
Yes. Well, I think the last thing to clarify is, well, you have so many things we can do from the TX to the RX. Where do we start? After talking to many customers in the field and who has really done the work, if you don't have a existing process, you would try to always start at the RX equalization. So you don't increase the system crosstalk level. You want to make sure that you are starting at the RX, configure RX correctly, then you can figure out your TX. Yeah, that's you know everything I know now.
Thank you.
Thank you.
Thank you for sharing this. Okay, I really hope I found it super interesting. I knew some of the things from because I created a number of videos on these topics. But for example, I really love the explanation about the eye. Uh, I never really looked at the eye this way, so now it's new start for me.
Oh yeah, we're all signal integrity detectives now.
Okay, thank you so much, Tim.
Yep.
And if you have any ideas for other topics, then let me know. And everyone who is watching, if they have any ideas for different topics, what we could talk about with Tim, then leave comments. Okay, thank you, Tim.
Thank you.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FEDEVEL online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.